Alright, Assalamu alaikum. Hopefully today is going to be our last class. So, we've been talking about the second law of thermodynamics and entropy, and we've come up with a nice argument that entropy represents a few things. It represents the number of available quantum microstates in a certain macrostate, and that is the entropy of that macrostate. It can also be characterized by the multiplicity of that macrostate. Multiplicity of a macrostate means inside that macrostate how many microstates exist. And this multiplicity was denoted by omega. How many states exist? So you have a parking lot, you have cars, energy that is going inside that parking lot. How many spaces exist for the cars to be parked inside that parking lot? The number of states that exist, available states, is how much a single car can spread out in that parking lot. So entropy is also a measure of the ability of energy to spread out. How much energy, how easily energy or internal energy can spread out. So this spreading of energy, this distribution of energy inside available microstates in a macrostate, this spreading out represents the S of the entropy. So, and traditionally, entropy was defined as the degree of disorder. But this is a misleading term. This disorder doesn't show you anything. It doesn't reveal the true physical picture of what entropy really is. So I avoid using this term, disorder. Alright, so disorder is an old-fashioned term, and it does not live up to the meaning of entropy. Multiplicity lives up to the meaning of entropy. The degree of spreading lives up to the meaning of entropy. Mathematically, if I know the multiplicity, I do know that the entropy of the system is natural log of the multiplicity, because omega is such a large number, it can be huge. In an equilibrium macrostate, omega is extremely large, astronomically large. Therefore, we would like to keep these numbers within our computational reach. We would like to compute with them. So we would like to make these numbers more saner. That's why you take the log of the number of microstates to give you a number that is more manageable. And traditionally, you would like to multiply this with a KB as well. So this formula actually is due to Boltzmann, and it's engraved on his tombstone as well. It's such an important formula. So this is the mathematical definition of entropy. But all of these different concepts show us what entropy really is. And the second law of thermodynamics is, now I would like to emphasize what is meant by law here. The second law of thermodynamics states that that a system would like to go to equilibrium. In a state of equilibrium, the system has maximal entropy. So every system would like to nudge itself towards the maximization of entropy. Alright? So if I have energy here, QA, which is the number of quantums in atom A, and there are many other in nanoparticle A or in solid A, and there are many other solids inside the system, C, etc. And all of this forms a closed system, which means energy can be exchanged in between these solids. But energy cannot be exchanged with an external, with any object outside this boundary. So all of these solids form a closed system. So if I would like to plot the energy inside A, which traditionally I am denoting by a number of quantums in A, but to be more precise or scientifically more literate looking, you would like to write this as UA, the internal energy in A. Okay, U is just a symbol for internal energy. We know that if I were to plot the multiplicity of the object A, there is a certain energy at which this multiplicity peaks. So I have some total energy inside the system. Some total energy is given to the system, U, and it redistributes itself within these solids, which could be of different sizes, different properties, different identities, and I would like to find out how much energy is actually shared by A. Then there's going to be a peak. The number of microstates at a certain fraction of the total energy, at this equilibrium energy, is going to peak up. So this is the most likely configuration of the system, because this number is so large, the peak is so big. This is what the second law of thermodynamics is. The most probable macro state has such a huge probability compared to other macro states that this turns out to be the only possible configuration. Something that has a probability that overwhelms everything else becomes the only possible configuration, because all other probabilities are almost zero as compared to this modal probability. Modal probability means maximum probability. And this is the second law of thermodynamics. The system would like to share its energy in such a way that the entropy of the system is maximized, the total system is maximized, and the multiplicity, wherever the multiplicity is maximum, that will be the equilibrium state. I'm going to give you more examples of this in a minute. So, this word law in the second law of thermodynamics, is this a fundamental law? Because when I am stating the second law of thermodynamics, you will realize that I am using that terms like the maximal probability effectively becomes the only probability. You see, if I showed you a video the other day in which a ball was descended from a certain height and was bouncing off the ground. So this is the motion of the ball, and it suddenly came to rest. Gradually it came to rest, sorry. Now, when it strikes the ground, it's transferring some of its energy to the ground. Alright, and as a result of this transfer, its own energy is decreasing. So in the next bounce, the height to which it ascends is smaller, because upon each collision with the ground, it has transferring some of its energy to the earth. So energy is being conserved in this process, because whatever energy this ball is losing is going to the earth is warming up slightly. However, energy conservation does not prevent you from the reverse process taking place. It's possible that this earth is a huge, big reservoir of energy. It has lots of energy. Why can't it transfer its energy to the ball? So the ball is static here. And this thermal motion of the atoms inside the solid can actually do work on the ball so that they can push off, so that the earth can actually cool up. Why shouldn't the earth cool up? And transfer some of its energy to the ball that is at rest, and as it transfers its energy, the ball starts jumping up, and going to a certain altitude. Now this is not violated by this first law of thermodynamics. The first law of thermodynamics, which is just the energy conservation principle, will allow such a process. There's nothing stopping you from that. But it's the second law of thermodynamics that tells you that you don't see this process in your real life. And the reason is that this Earth is such a large object as compared to this ball that the number of available microstates inside the Earth is humongous. It is astronomically large because there are so many atoms in the Earth as compared to the ball. So energy would like to spend itself, would like to spread out in the Earth rather than in the ball. So it would like to go to the Earth, because that will maximize the entropy of the system. If all the energy were concentrated in the ball, the number of available microstates in the ball is smaller. So entropy is not on its maximal value. If entropy would like to be on its maximal value, it would like to remain in a configuration which has the maximum freedom available for maximum number of places for the energy to go. And that can only take place when the maximal amount of energy is distributed inside the Earth. So energy transfer from the ball to the Earth can take place, not vice versa. But the vice versa process is not prohibited by the fundamental laws of physics. So the second law of thermodynamics is not as fundamental a law as the first law of thermodynamics. It's a law because it's difficult to look at materializations of contrary situations, which means that nature behaves this way in most of the cases. Almost exclusively in this way. It's difficult to find deviations from this empirical behavior because the number of microstates in the equilibrium state is so large that all other possibilities diminish to almost zero. So it's not as fundamental as the first law of thermodynamics, which is just the law of conservation of energy, but still it is so important and it has become so realizable that it has been exalted to the status of law. Okay, so I hope you understand this. Now, let me look at an example. Simplest example that we see in nature, we open a bottle of scent and the perfume spreads out in this room. This is also the maximization of entropy because the scent molecules would like to spread out in the available space, because in the available space they will have a greater degree of spreading out, they will have a higher multiplicity. For example, let me simplify this problem in the following fashion. I have a container which has two compartments in it, and these compartments are separated by a wall in the middle of the container. Now I have some perfume molecules here. They are only inside this compartment. Okay? And this compartment is devoid of these molecules. So what I slowly do is I take this wall and slowly take the wall out of the container. I just slowly take it out. Now what's going to happen by empirical observation is that these molecules are going to diffuse out. So this wall is receding from the container, it's going out. And as this takes place, these molecules, gas molecules, now have the ability to meander into the other half of the container. So they will go out from this container and they will like to spread out. Intuitively, this is just a second law of thermodynamics because it's the same energy. The energy of the system is not changing. Now, the energy of the system is not changing, which means the U, which is the internal energy, is fixed. So if I put a thermometer inside this chamber, this is the level of mercury. As I pull out the wall, the thermometer does not show a change in its reading, which means the temperature doesn't change, which means that the internal energy doesn't change. The temperature is just the average internal energy. So this container neither heats up nor cools. And that's why I have to pull this wall out slowly. It's because I'm pulling out this wall extremely slowly that the temperature doesn't change. Okay? So this is an isothermal process. It doesn't change the temperature. If I pull down this wall abruptly, this gas is going to expand and it's going to cool. This is an adiabatic process, but I'm not going to go into these details. But I just pull out this wall slowly, so at all instances the system remains at the same temperature. But these molecules have now diffused out into the entire volume. Now they're occupying twice the volume. But the total volume of the container remains fixed. Now this is increasing the entropy of the system. Okay, and that's why this is going to happen. The second law of thermodynamics dictates that this diffusion is going to take place because now the molecules have more space to go. Now, suppose I would like to quantitatively find out what's the increase in entropy. I'd like to do a quantitative calculation. Okay, because as scientists we would like to be quantitative about our physics. Intuition is good. Everyone could tell you that these molecules are going to diffuse. And it seems that since these molecules have greater volume to go into, they have more space to go into, they have more freedom, they have more available microstates, so they would go there. But let's do a quantitative calculation, a basic calculation here. Now if I just hypothetically do a thought experiment in which if a molecule is here, then this state, let's call this a quantum state in which the molecule is in the left compartment and it's absent from the right compartment. Let's denote this microstate. This is a microstate by this label. This is a label. This is just quantum mechanics. Can you see? Can you see what's going on the blackboard? Nazar aa raha hai? Alright, so this is just a description of this configuration. This is a microstate. Now if I open this wall is pulled out. Then would the number of microstates go up? Available microstates, would it go up? Yes, it will be double the number. If I pull out this wall, this molecule could be in the left compartment and it could be in the right compartment, or it could be in the right compartment. And both of these configurations, which are called microstates, have the same energy. They are degenerate. So now if I took out the wall, took out the separation, the partition, two microstates become available and they are 1, 0. This is 1 microstate and the other one is 0, 1. So the number of microstates has doubled. If I had two molecules, two gas molecules, and I take out the wall, how many microstates would exist? 4. Both of them could be here, none could be here. So I could have 4 microstates, which are 2 in the first compartment, 0 in the second compartment, 1 in each. What else? I could have 1, 2. Suppose these are distinguishable molecules. Alright? Suppose these are distinguishable molecules. This is a classical gas. So these molecules are distinguishable. Okay, so it's a classical gas, it's not a quantum gas that we're talking about. So there are two kinds of 1, 1. Which means this molecule could be here, the other one could be here. But this molecule, but they could swap their places as well. It's not a quantum gas, this is a distinguishable ensemble of molecules. I can look at this molecule and keep tracking it. Okay? So I have 4 configurations. So with 2 molecules I have 4 configurations. With 3 I will have 8. With 4 I will have 16. With n molecules I will have 2n configurations. So the multiplicity is going up. If my now I have a large number of molecules. If my original multiplicity was say some value. I don't know the original multiplicity because I don't know the number of molecules in the. I know the number of molecules in the gas, but I don't actually know how many microstates are available, because the microstates are not just the compartments. I'm simplifying the problem by bifurcating the compartment into two, but there could be. I could break up this problem into an infinitely large number of compartments. So my original multiplicity, whatever it is, let's call it omega naught. Now if I take out the wall, my new multiplicity is going to increase. What's the new multiplicity? It's the original multiplicity multiplied with some number. What's the number that we need to multiply it with? 2. If I have n molecules, it's 2 raised power n. So my new entropy, as I pull off the wall, my new entropy is Kb natural log 2n omega naught. So my entropy has gone up. So let's see if it's actually gone up. I can break this up as Kb natural log 2 raised power n plus Kb natural log omega naught. But this is nothing but the original entropy. This is the original entropy before I've taken out the wall. So the increase in entropy is given by Kb natural log 2n. The increase in entropy is Kb natural log 2n, which I can also write as n Kb natural log 2, where n is the number of molecules. So the entropy of the system goes up. I don't need to worry about what my original entropy is, because entropy, as you can imagine, is a difficult quantity to measure, because you can't measure the number of microstates in a system. How in the world are you going to tell how many microstates are in this compartment of volume V? You don't know. It's impossible to measure n. You don't have an analog to a thermometer which measures the temperature. You don't have a device that measures entropy. So what at best you could do in most cases, you can find changes in entropy. How much does the entropy change? And we know that for closed systems, by the second law of thermodynamics, it always goes up. Okay? So this entropy, this diffusion maximizes the entropy, and now we have a quantitative argument as to why it does so. Now let's come back to the original problem. Any questions about this? Yes. ये n कहाँ से आया है? ये वाला? So if I have, so there's a property of logs. Any more questions? Yes. Because these are two distinguishable particles. One is, let's call them, one of them A, the other B. This is not a quantum gas, it's a classical gas that we're talking about. Yes.
So if we are in a closed system and there are only two particles and we decrease the temperature to almost 0 Kelvin, will we then see the lower probable microstate, or we don't see the normal physical process?
So if you decrease the temperature of the system,
and there are only two atoms interacting in
so the system will go to its ground state, and if both, now it depends upon whether you're talking about fermions or bosons. If they are fermions, they can't be in the same state, so the entropy. So if all the molecules are in the same state, all of them are in the same state, the entropy is going to be 0.
No, I mean, will we see lower probable microstate? Because you said that if we are only talking about two atoms, the lower probable microstates are still there.
We'll see lower probable macrostates with smaller numbers of objects. For example, we looked at two atoms interacting. In nanotechnology, when you do nanomaterial synthesis and you're dealing with small clusters of atoms like dimers or trimers or polymers and single molecules, then you see these effects. You will see macrostates that do not have the maximal probability. Yes. Otherwise what's going to happen is that the temperature is going to go down of the system. I don't want to do that. We want to do an isothermal process, not an adiabatic process. Yes. Diffusion is observable at 0 Kelvin. Yes, there is always going to be some Brownian motion even at 0 Kelvin. Yes, it is observable. But only if you could achieve 0 Kelvin. This is unachievable. Alright, so let's move on. Let's move on to our original discussion of having a hot object in contact with a cold object. Now, suppose, first of all, let's suppose I have two identical objects. One is hot, the other is cold. So here is my diagram. So I have a cold object and a hot object. And these solids have the same mass, they are the same material. Now if I were to plot the entropy versus the energy of each solid, the graph is going to be the same. The entropy versus the temperature graph is going to be the same for each solid because these are just identical solids. And what does the entropy graph look like? It's a concave graph. A concave downward graph. So I have energy here. Let's call this object A, let's call this object B, UA. And this is the entropy of A. And the graph is concave downwards, concave down, so it's going down. So this is the graph, and we plotted this graph. Okay, so of course, higher the energy, higher the entropy is. Okay, now the point is that why is the entropy higher? Because the multiplicity omega goes higher, and the formula for the multiplicity in the numerator there is a n plus q minus 1 factorial. As q goes up, the multiplicity goes up. Okay, so I hope you do agree with me on this. This is something from the previous lecture. Now if I have an object B, the graph for object B is going to be identical because A is just the same as B. So I can just plot the graph for B here as well. UB, SP. Now this is the entropy of B versus the energy in B. So this graph describes the behavior of this object. How does it behave? Higher the energy, higher the entropy is. Now this is the energy inside the object. Okay? Any questions about this? You have to be absolutely crystal clear about this before we proceed. I hope your question doesn't add to the confusion of what the other students, but please do ask. How are we? So this is what we did in this is omega. This is the natural log of omega. Remember in the previous lecture we were looking at the number of quantums in a solid, and then and we plotted the omega with respect to this. QB, okay, you want to call this QA, fine. You want to call this QB, fine. But I would like to call it U. U is the energy. Q is just the number of quantums. That's the same thing as the energy. Okay? Any questions? Any further questions? Yes.
The energy of object A is equal to energy of object B.
No. If this is hot, this has more internal energy.
So this should be
So this is a hot object, this is a cold object. Which one of these objects has more energy? B has more energy. So B lies somewhere here on the graph. Okay? At time 0. Before energy exchange has taken place. whereas A has smaller energy. So A lies somewhere here on the graph, okay, at time t equals 0. So it's the same graph that describes the behavior of the same object, and initially object B has a higher energy because it's at a higher temperature. Object A has a lower internal energy, it's at a lower temperature, so it's somewhere towards the origin on this graph. Yes?
Sir, does this slope ever become or approach 0?
Not in this case, but for the total, yes. Okay, we'll see this in a minute. Any more questions? Alright, so now so initially this is a cold object, this is a hot object. Hot object means B starts off on the graph at a higher point. This A starts off on the graph at a lower point. Okay, so it's a nod of affirmation. Now what we would like to do, since these are identical graphs for both the objects, what I would like to do here is I would like to plot U and some energy and entropy here, and this can correspond to object A or B. Since object A and B are the same, I would like to draw the same graph for both objects. Now object A, which is at a lower temperature, starts off here. This is object A. And object B, which is at a higher temperature, starts off here. So these objects start off on different places on the entropy versus energy graph. High temperature, low temperature. Okay? Now intuitively, if you were not a student of physics, you could tell the answer to the question as what's going to happen. Energy is going to transfer from the B to A. So its internal energy is going to go down. Object A's internal energy is going to go up. Now if that were to happen, if B's energy goes down, this means its internal energy has to decrease. But A's internal energy has to go up. Now if you look at this graph has the property that it is concave. Concave downwards, it's going down, so it's concave downwards. Now this graph has different slopes at different points. Now this is the nice, beautiful thing. Let me just raise this thing for a minute so that you can easily see what's going on. Now the slopes are different of this graph, and slope is important. As I mentioned, it's related to the temperature. Here, for the cold object, this is the slope. If I just draw a tangent to this graph, this is the slope of this graph. At point B, the slope is totally different. At point B, the slope is flatter, it's smaller. So the slope constantly changes for this graph. Now what is the slope? If I draw a slope, the slope just represents a triangle. I can drop a side of the triangle here and a side of the triangle here. So these are two sides of a right angle triangle. The slope represents this angle here. It represents the ratio of this side and this side. That's what the slope is, the tangent of this angle. It's this side versus this side. Now on this graph, this axis represents energy. So this is some change in energy. This axis represents a change in entropy. So higher the slope, so if I were to draw a triangle with the same internal energy change, but the slope is higher. I need to draw a steeper graph, which means that for the same change in internal energy, the change in entropy is higher. So the slope represents how does the entropy change when the internal energy changes. Agreed? Slope is flatter, the entropy doesn't change much if the internal energy changes. Now for object B, we would like the internal energy to go down. Okay? So if it loses its internal energy, since it's a closed system, energy is not coming from the environment, from the universe into A and B, and it's not going from A and B into anywhere else. It's a closed system. So the energy that comes out from A must go into, that comes out from B must go into A. There's nowhere else for the energy to go. So if the energy here drops, the energy here goes up by the same amount. But the change in entropies are different because the slopes are different. So now if I were to look at this point here and I would like to have a small change in energy. So what I do, I look at this slope here, and at this point I have some small change in energy, delta U. Let me redraw this figure over here. Just, you don't have to do this, but let me try to do a more accurate figure. So I've drawn a triangle here, a small triangle. This side represents the change in energy of B, and it's negative, which means that the energy of this system is going down. The energy of this B is going down, which means it's going down this curve. This energy is dropping, and the change in entropy, delta S, which is negative here, because now you're going down the graph. Since you're going down the graph, this is negative here. The change in entropy is negative because the entropy is falling. The entropy is falling for a corresponding change in internal energy. The internal energy goes down, so this point moves towards the left, towards the origin. As its energy goes down, because of this side of the triangle, its entropy goes down. So it's going down both in energy and as well as in entropy. So the entropy of this object is going down. However, this energy must be transferred to object A because there is nowhere else for the energy to go. So I can draw a triangle here whose side on the horizontal axis is of the same length as this delta U. So this length is the same. Its energy goes up by the same amount as the drop in an energy of B. But now if I were to look at the slope, the change in entropy, which is positive now, delta S is now positive for object A, it's negative for object B. For the same amount of energy, the entropy of the system A has gone up by a larger amount. Because the slope here is larger. It's a steeper slope here. So now energy is being transferred from B to A. The energy of B is going down, and the energy of the entropy of B is going down, and the entropy of A is going up, but the increase in entropy of A is greater than the decrease in entropy of B. So if I were to look at delta S, which is the total change in entropy of the system, this is delta SA, the change in entropy of A, plus delta SB, the change in entropy of B, but this object here is negative. But it's small negative. And this is large positive, larger positive. So overall delta S is positive. The entropy of the system is going up. Alright. So as I move further, as this point, as object B moves down this graph, and object A moves up this graph, energy exchange is continually occurring between A and B, and as a result of this energy exchange, its entropy is going up, its entropy is going down, but in each step, delta S is always positive, because this point is further towards the right, and because since this is a concave graph, the slope here is always smaller. And that's what a concave graph is. In a concave graph, the slope further away from the origin is smaller. This is what a concave graph is. So since the slope here is smaller, the decrease in energy is more than compensated by the increase in energy of A. Eventually, both of these solids reach a point where, so if object A reaches here and object B reaches here, you don't want to go beyond that point. Because if you were to go beyond that point, A's energy will be increasing, because beyond this point the slopes are bigger. Now if object B loses more of its energy, the overall entropy of the system is going to go down. So equilibrium is established when the overall entropy of the system has reached its maximal point. So if I were to plot the total entropy of the system, so this is my U, this is my total entropy of the system, this is the entropy of A or B. At a particular point, the total entropy of the system is going to be maximum, and then it's going to drop again. So this point of maximal entropy is when energy transfer between A and B ceases. Because beyond that point, the decrease in entropy will outweigh the increase in entropy. There will be more decrease in entropy. And this is when equilibrium is being established and energy transfer between the two objects ceases and the system comes in a state of equilibrium. Okay? Now, what is this temperature? This temperature is just going to be the mean of these initial and the final temperatures. It's just going to be in the middle between this, in the middle. It's not exactly the middle of the entropy graph, but it's in the middle of the temperatures. And that will correspond to a certain point on this graph. Now the key thing is, any questions now about this? Yes.
When you say that the entropy reaches equilibrium, you mean that delta S should be 0 or the differential of S should be 0? When it reaches the equilibrium.
So, in the state of equilibrium, the slope of the total energy remains is 0. Okay, that's what it means. That means to do a mathematical connection between entropy versus internal energy, that is slope of this graph and temperature. But is this discussion clear? Forget about the quantitative. Is this discussion clear on a graphical scale?
So for small
First, is it clear? Besides that single question. Yes.
for small
For small?
decrease in entropy in the water object, we have a large increase in the water object. Is that because we have more microstates available in the
No.
water object?
No, the number of microstates available is the same. It's just that the slope of this line is bigger here. You increase the energy by some amount. This point goes higher up on the entropy graph. This point is decreasing, it's decrementing, it's descending on the entropy graph. This point is ascending on the entropy graph. The ascent is higher than the descent. And why is that? Because of the shape of this graph. The shape of this graph has to be concave. If it were convex or anything else, this behavior would not be true. The second law of thermodynamics depends upon the concavity or the shape of this graph. Otherwise, you would not have this scenario here.
It
Just imagine that if you have a hot and a cold object and they were transferring energy and you had a graph of this kind. This is U, this is S. Have a graph of this kind, a convex graph. And then see what's going to happen. Then what's going to happen is that if you have a hot object here, its energy goes down, this is the change in the entropy. You have a cold object here, its energy goes up by the same amount, but the increase in its entropy, delta SA, is smaller than delta SB, so the overall decrease in the entropy of the system is larger. So this convex graph will not hold water against the second law of thermodynamics. This is not going to hold true. The second law of thermodynamics depends upon the concavity of this graph, upon what this graph looks like. And actually I showed you what this graph looks like in the previous lecture. Now look at this example. I have an object which is cold of some size, but this object is now placed in hot air in the environment. So this is inside hot air. Now the object which I am going to discuss and the air, they are two different kinds of objects, they are different sizes, there are different number of microstates are inside both of these objects. Now we treat the hot air, the environment, as a reservoir. What is a reservoir? What idea is brought into your mind when you think of a reservoir? What's a reservoir? Huge area. You take something out from it, its volume doesn't go down. You put something to it, its volume doesn't rise. This is what a reservoir is. Okay? Now let's treat the hot air as a reservoir, which means that if you take energy out of the reservoir, its temperature doesn't change. That's what a reservoir is. मिले समंदर से प्यासे को शबनम. अगर समंदर से किसी प्यासे को थोड़े से पानी मिल जाए तो ये कोई समंदर की सेहत पे फर्क नहीं आता. This is what a reservoir is. Now if you take energy out of a reservoir, its temperature doesn't go down, and if you add some energy to the reservoir, its temperature doesn't go up. So how on earth would I like to model such an object? So this is my energy, this is my entropy. The entropy changes. If I add something to a reservoir, its entropy changes. If I take something out, the entropy changes, but the temperature doesn't change. So what kind of graph do you think a reservoir should have? Or the entropy versus the temperature? Straight line? Straight horizontal line? Straight vertical line? Straight sloping line? Vertical line? It should be a sloping line, straight sloping line. This is the reservoir. Which means energy goes down, the entropy goes down, but the temperature doesn't change. And I'm telling you that I'm predicting that the temperature is related to the slope of the entropy versus the energy graph. Okay? So this is a reservoir. This is my air, hot air. Now you could be hot or cold, you could be on different points on this graph. Yes?
This graph is changing just say for A and then Y are
The changes in temperature are not the same. I'm going to put temperature into the equation after the break. Okay? No, because the temperature is related to the slope of this graph. The slope is constant here. Now my object, my solid object has a concave graph of this kind. This is my solid. This is my air. Now there is a slope here, and my solid is cold. For clarity, let me redraw this line in a bit more clear, in a clearer fashion. So now if I look at this, my object is cold. There is some slope over here. My air is hotter. Somewhere on this graph, it's hotter, right? But if the temperature of the air doesn't change, so because this slope is the same, so this object, the air could be anywhere on this graph. Entropy could be anything. Now, if this solid is cooler than the air, it must absorb energy from the air. So this object must increase its internal energy. So it must move on the right on this graph. Its internal energy must go up. Its internal energy must go up. Its internal energy must go down. So initially, this graph, the process is going to start, for the cold object is going to start from the left, and for the hot air it's going to start on the right. Its internal energy must go up, its internal energy must go down. Now when its internal energy goes up, its entropy goes up. So increase in internal energy, delta U A, this is delta S A, its internal energy goes up. Now where is this energy coming from? It's coming from the hot air. So its energy is going down, so it must move on this graph towards the left. So the hot air moves, this takes a trajectory, it moves towards the origin, and in the process, its entropy, delta SB, let's call it B, goes down. Now this slope is higher than this slope. This slope has to be higher than this slope if this transfer of energy from the hot air to the cold object is going to take place. Which means that this slope must be smaller than the initial slope of this cold object. Only then will energy transfer take place from hot to cold. Now its internal energy goes down, its entropy goes down, and this point moves up. For the cold object, it moves up. And this point for the hot air moves down. So this is moving downward, this is moving upwards. Now, energy transfer will cease when the hot object comes at the same temperature as the cold object. When the hot air and the cold object equilibrate, they reach the same temperature, and that is going to happen, of course intuitively, graphically, that is going to happen when this cold object on this graph reaches a point where the slope is the same as this slope. So I take a point on this object where the slope matches the slope of, it looks like this point. When this slope here on this object matches the slope of the hot air. So this object is going up. This object is decreasing its internal energy. This change in internal energy has to be the same as this change in internal energy. So if I were to plot these graphs correctly, it will turn out to be the case. So in any case, the slope of this graph reaches a point where the slope equals the slope of this graph. And that is when the two objects are at the same temperature and equilibrium is established. If you go beyond that, then there will be a total decrease in the total entropy of the system. And that is not allowed by the second law of thermodynamics. Okay? So after a break, I'm going to show you some more graphs. So when I draw on blackboard, there are always these inconsistencies because after all I'm a finite human being. But on a graph, the graphs that you will get will show you the actual situation of what's going on. Let's take a 10-minute break.